In this video I will show how I try to improve my reference oscillators for phase noise measurements. What you see on screen now is a frequency shifted rubidium source. Frequency shift is obtained by dividing 10 MHz, which is from that rubidium source, by a factor 512. That's about 20 Hz. So mixing it in quadrature to get a signal 20 Hz below 10 MHz gives the signal that I'm going to use for phase locking of better oscillators than I have used before with the same method. And as you can see, the signal is very noisy. And if you look here, you can see the noisiness, that the dots are spread over an interval of about 0.1 millihertz. This is 15 seconds per pixel. When I switched on 6.5 hours ago, the curve started at 0. So the total frequency drift is 1.2 millihertz over 6.5 hours, and the curve is not quite flat yet. And what is interesting is to see the extreme precision of the green trace. It doesn't look noisy at all. It is my Wenzel oscillator, which I'm using as the channel 1 oscillator for this measurement. I will change the time scale and allow this to run for some more time. There is a limit on how long time per pixel. The maximum is 32. I didn't think I would need more than that when I wrote this code. And I also reduced the bandwidth for extraction of the carrier. And I can reduce it further by making a larger transform size in the baseband. It makes things run slower, of course, but it will reduce the noise that I will see on the carrier. The phase noise at 0.01 Hz is at minus 32 dBc per Hertz. And this is about 100 seconds then. After 7 more hours, this frequency versus time graph is still increasing slowly. After all the 7 hours, the frequency has drifted from minus 0.2 to plus 0.6 millihertz. And probably this is the Wenzel oscillator that is drifting slowly, but it could also be the rubidium. I don't know. The Wenzel oscillator, the green trace, is really very stable. I cannot draw any conclusions from this because the width of the lines, due to the noise close to the carrier, is too large. But I can look at the Allen graph. That's suitable for this kind of evaluation. There is a minimum at 400 seconds, and then the Allen deviation starts to grow. And I look at the green and yellow because that is the Allen with the rubidium oscillator versus the Wenzel oscillator. The red is my own channel 2 oscillator, which is almost a factor 10 worse at 500 seconds. And you can see at 4,000 seconds, the red and the green are the same. That is because the channel 2 oscillator is phase locked to the Wenzel oscillator. I can conclude that I would have to lock with a time constant of something like 200 or 300 seconds to take advantage of correlation up to 0.01 Hertz or even 0.001 Hertz. If I can make an oscillator stable enough for that. And then, whether locking it to the rubidium oscillator or to the Wenzel oscillator is not really something that I know which would be best. I have used this oscillator before to lock it against the rubidium source. It is not particularly good. I designed it originally for use at the frequency of the Wenzel oscillator and then shifted just by putting some big capacitors across the crystal. The sideband noise at 1 Hertz offset is minus 119 or something, and at 0.1 it is about, hard to say, minus 93 perhaps. It has not converged properly, and here it is far from convergent. So I need an improvement in the order of 10 decibels at least. And you can see here the green trace is the noise it produces. Because now I know that the Wenzel oscillator is very flat. And the scale is 0.4 millihertz per division. So this is 0.4 millihertz, or a little bit more than that. The reason why I want the frequency off from 10 megahertz is that I need a bigger separation between the tested object and the reference oscillators. That is to have a higher audio frequency in the direct conversion receiver that I'm using here with Linrod. That is placing the zero frequency at about 30 Hertz, because the Wenzel is about 10 Hertz above 10 megahertz. With a 30 Hertz offset from zero, I can accurately measure phase noise up to 29 Hertz. And now it's only up to 9 Hertz with the Wenzel oscillator. Because I need the Wenzel oscillator for tuning the oscillators that I am working with. And another thing, with 30 Hertz offset, overtones come every 30 Hertz, and this means I can measure offsets up to a kilohertz or more by looking at the noise floor between these spurs that come every 30 Hertz. I'm running the unit as a selective amplifier. Here is the frequency response. The frequency is 20 Hertz below the calibration of this network analyzer, while the Wenzel oscillator is at plus 18. So that gives a good frequency difference. Now, what is the bandwidth? Is very sharp. Q is 1.33 million. This is odd, but this is what I see. And when I span a wider range, it looks like this. And I just discovered this artifact. If I span too quickly, now medium narrow bandwidth, it looks like this. I had a little problem before I discovered what the reason was. Narrow bandwidth, then I don't see it. Not much. I have removed capacitors to restore the original configuration of this oscillator. Now the frequency is plus 19. So it's 2 Hz above the Wenzel oscillator at the moment. If I look at bandwidth and Q is still 1.3 million, a little bit more. And the loss is about 10 dB. So this is similar to before. The old crystal is one of these from Bell Labs. I will replace it with this group of 4 parallel crystals. It will fit into the same oven. Some copper will provide mechanical stability and make this unit fit into the hole that previously held the old crystal. So good heat contact with the oven and mechanical stability should be provided by the copper. Here the 4 crystals is in place in the oven. I will put back the thermal isolation around it. I have tuned the group of 4 crystals very close to the frequency of the Wenzel oscillator, because I want to investigate the unit as an amplifier as a first step. And now it is running as an oscillator. I applied feedback from the limited output, and the power there was not enough to give full signal level at the crystals. The level is about 3 decibels below the 4 milliamps that I want to have. And that should give about a 3 decibels loss here on the wide noise. And that's not what I'm interested in at the moment. I'm looking for the noise at 1 Hz offset primarily. And I know that a single crystal in a good oscillator with very low amplifier noise could give minus 123 dBc per Hertz. And with 4 crystals, I might hope for 6 decibels lower crystal noise, would be minus 129 down here. And then I would want the amplifier noise to be 6 decibels below that. That would be minus 135. And this means that I need nearly 20 decibels lower noise from the amplifier. Now, at this point, the slope is 30 decibels per decade, and that originates in the flicker noise of the amplifier. So I could say that I want the noise at 10 Hz to go down by 20 decibels. The idea is that the F-2 flicker noise with this slope is amplified at 1 Hz due to the feedback. So I need to bring this line down, and then this curved line will follow down also. This is the crystal filter. The output impedance is resistive 22 ohms, and the tuning capacitor is in the order of 27 pf. I don't remember. It's a fixed capacitor because large tunable capacitors are easily creating noise. And this is the coupling, and this is to get a good suppression in the stop band. This is the current amplifier, two BF240 in parallel. They have independent base supply voltages through voltage dividers with fairly low impedance, so the thermal noise should be negligible on the basis, and of course independent, since there are two separate. And then they have each one its own emitter resistor, so the currents through the transistors should be uncorrelated, which should lower the noise by 3 decibels. Now, that is not enough at all. This thing gives far too much noise. And what comes after is unimportant at this point. The input impedance with the load that is applied normally is 7 ohms. And that's fairly nice for a 22 ohms output impedance of the crystal. It means the crystal is not much loaded. To analyze the amplifier and the crystal filter or any other part of the system, I use this setup. The Wenzel oscillator, which I now know is very good, has to be amplified to get enough signal level for the purpose. And then I have a 3-way splitter that isolates the 3 outputs. One of them goes to the reference input of the PN2060. One of them goes to the device under test, which is then the output split with an hybrid for the DUT1 and the DUT2 inputs of the 2060. And then the third output is used for a PLL to the channel 2 oscillator. So it follows the frequency of the Wenzel, but very slowly. So within the range of interest now, down to 0.1 Hertz, they are independent when it comes to the noise. And it is the input to reference 2. The beauty of this thing is that it is an interferometer. If I replace the device under test with just a simple through wire, I have the same signal on the reference 1 and on the DUT 1, which means that any frequency modulation from the Wenzel oscillator will not be present here in the difference frequency between those two. And the other channel will have the noise of this oscillator, but since this is a correlation system, there will be no correlation of the signal that is taken as the difference between these two and the difference between these two. This contains the noise of the Wenzel, the 2 difference, but since that is not present in the 1 difference, it will not contribute to the average correlation spectrum. For measurements through the crystal filter at frequency separations from the carrier below about 1 Hertz, the passband is so flat that the noise suppressed by the filter is negligible, down to something like 10 decibels. But at higher offsets, of course, the noise from the Wenzel is removed by the filter. I have made a couple of phase noise measurements now. The top line is the oscillator measurement you have just seen, and the next line is running the unit as the device under test in the interferometric setup with the PN2060. And the first row here is with nothing, means a BNC to BNC female adapter. And that's the limit of my test system then. The next measurement is with the unit as a selective amplifier from the input on the crystal to the normal output, the power output. And then I have fed the signal through the crystal and the first amplifier stage, but not through the secondary amplifiers. And the last line is the first amplifier only, fed from a 22 ohm source. Looking at the noise at 1 Hz offset, the oscillator runs at -116, and the system performance says -139. And the observed noise when I feed the signal into the crystal and take it out from the normal output or the limiter output, or at the first amplifier output, or use the first amplifier only, all the time I get the same value, -129, which means this is the performance of the amplifier itself and has nothing to do with the crystal. The oscillator noise, that means -116 dBc per Hertz, that is caused by the noise of the amplifier, and it is amplified because of the feedback. So the amplifier noise that generates this level is at -129 dBc per Hertz. That's a difference by 13 dB. This may be influenced by how the coupling to the crystal is arranged, because the power output from the limiter is a little bit too low, so I may have loaded the crystal a little bit too much. If that is true, this difference would be a little smaller if I had more power from the limited output. But that's a small thing. The target for the amplifier noise floor I get is -123. That's the value a good amplifier gives with a good crystal. -6 decibels, because I have 4 crystals, and then -6 more decibels, because I want the noise from the amplifier to be 6 decibels below the noise from the crystal. That means that the target noise floor at 1 Hz offset from the amplifier is -135 dBc per Hertz. So I want to improve by 16 decibels. The experiment with the BNC to BNC adapter showed -139, so I should be able to see -135 clearly. But reaching there may be rather difficult. Here are the component values I didn't know before I opened and checked in the box. So with 4 milliamps, which is the maximum current from crystals, and they give 22 ohms output impedance, so I feed from a 22 ohm resistive source, and that gave me -129 dBc per Hertz. I replaced the two BF240 by a single BFR91A. To get the 7 ohm impedance I want to load with, I had to reduce the supply voltage down to 5.0 volts. And then the amplifier saturates if I go above about 2 milliamps. So I measured the noise at this signal level. The phase noise at 1 Hz offset is a little higher now, and the table says -126 dBc per Hertz. When I increase the supply voltage from 5 to 16 volts here, the impedance on the emitter becomes much lower, and that means that the transformation ratio 2:1 gives a suitable input impedance, a little bit higher, 11 ohms instead of 7. But performance is not very interesting. The noise is higher. At 1 Hz it is minus 122 dBc per Hertz. And the noise is a straight line, about 11 decibels per decade over a wide range here. So this is not the way to go. I have reduced the power by 10 decibels. And the result, as you can see, is dramatic. There is no longer 11 decibels per decade, it's much steeper. And at 1 Hertz the noise is now minus 124 dBc per Hertz. The reason for this difference is that the amplifier was saturated before. It was compressed by about 5 decibels when running the full crystal current into the BFR 91A. I have reconfigured the crystal filter. This is what I had before. Now I have changed it like this. It means I am using the high impedance point on the top of the crystal, where the impedance is a couple of kilo ohms. And the same tuning capacitor and the same coupling capacitor. And there is the same current through the crystal. But now I am not taking out the current from here, I am taking the voltage from here. And this transformer is to make the stop band attenuation better by adding in antiphase the voltage that comes outside the resonance of the crystal. I have added a resistor, half a megohm, and 10 nanofarads coupling capacitor to make sure the voltage on the crystal is 0, and this will not load the Q because the impedance is more than 100 times below half a megohm. This is the first amplifier I'm trying. It's a source follower with a single J310. First, a step-up transformer to increase the voltage by a factor of 2 means the impedance a factor of 4. This resistor is to kill oscillations at about 70 MHz. The impedance is so high so I don't think the loss through 360 ohms matters at the signal frequency, but I will check that later on. I could find some better way of killing the oscillations. This capacitor is selected to give the same crystal current and Q for the filter as when I have this not connected at all. So it means that the impedance is maximized. If I make this capacitor bigger, I get the negative resistance at this point and the Q increases, and that's not what I want. I think that generates noise. Anyway, this is what I am running at the moment. Here is what I see after more than 30 hours. I'm feeding the Wenzel oscillator through the selective amplifier and analyzing with the Wenzel oscillator as the reference in one of the channels. What I see is a straight line, I think, like this, and that is the amplifier noise. And then there is a hump here which I attribute to the variations in the gate to drain capacitance of the source follower. I have seen this before, and it can be removed by forcing the drain to follow the gate. The reason I'm doing these things is I need a better reference oscillator for my main project, which is to optimize the noise of the 21 crystals in parallel oscillator. And I need far too long measurement times, so I need better reference oscillators. And I intend this to be one of them. The circles here tell me that the result is not reliable. I have not waited long enough. But it is enough to see that the noise at 1 Hertz, including the noise from the gate to drain capacitor, is minus 130. So I will proceed. Next step is to measure the noise of the amplifier without the crystal filter. Here is the input impedance and frequency response of the selective amplifier that I'm testing. I have placed a 3 kilo ohm resistor from the amplifier input, means the midpoint of that step-up transformer, to ground. And this has caused a loss of 6 decibels. I can look at the difference here, 5.8. So the impedance in this point is 3 kilo ohms. Means I will feed the amplifier from a 3 kilo ohm resistive source. Here is the phase noise of the amplifier only, the source follower. It is a straight line, more or less, like this. And here is what I had with the crystal filter in place. And we can see that the input impedance when the crystal is there is lower at the 50 Hz offset. And that explains, I think, why the phase noise is lower. But at 1 Hz, these are very similar. I have reduced the signal level by 6 decibels and removed 5 decibels of attenuation in the analyzer, so I have a similar signal level into the PN2060. And the result is somewhat unexpected. The phase noise is 5 dB higher, or maybe 6. I didn't expect that. Of course, here in the flat region, I expect the noise to go up as the carrier goes down. But why this phase noise stays at a constant amplitude while the carrier is reduced? This is something I don't understand. I have reduced the supply voltage from 16 to 10 volts. That has reduced the power from 230 milliwatts to 103 milliwatts for the source follower. 20 milliamps, 11.5 volts, and now 15.6 milliamps and 6.6 volts for the transistor. And the result here is a little bit better. This was at the full power, and here is what I have now at reduced power. Note that the time is about half. It is 600 averages here and 1070 here. But there is clearly a small improvement. Particularly easy to see here. Here statistics is not good enough. But still one can see that it's about 1 dB or perhaps 1.5. So it is not a big difference. But one of the things that has happened is that the output impedance has become larger, which means that the signal level has dropped by about 1 decibel. Here is the frequency response when I feed the source follower through a 3 kilo ohm resistor. I have now shorted that 3 kilo ohm resistor, so it is fed now directly from the 50 ohm source impedance of the network analyzer. And as you can see, the difference on the peak is very small. It means that the input impedance is very high. With a source impedance of 50 ohms, the phase noise is much lower. It is below minus 137 or something. And note the circles everywhere. So it's below what I can see with this test system. And the slope is steep, so it's even better here at 10 Hz. I can compare with what I had with a 3 kilo ohm resistor in series. Is here. The difference is more than 10 decibels at 10 Hz offset. But what it is at 1 Hz, I cannot say. But it is much better. I have changed the biasing of the source follower. Means I made this resistor twice as large to bring up the gate voltage. And then I need a bigger source resistor. Now the drain to source is 8.5 volts and the current 16 milliamps. And this is fairly close to the operating parameters I had when running the unit from 10 volts for the power supply. The difference in noise performance is very small. But now I have added a second input, means I can set the signal in here and leave this one open. And I have done that. This means that the impedance feeding the gate of the FET has dropped from 12 kilo ohms to 3 kilo ohms, well, plus 360 ohms, because I feed through the same 3 kilo ohm resistor that I used before. Here is the noise I see feeding directly to the gate of the source follower. The previous situation was this, and it's clear that the noise is significantly lower. Not as low as when feeding with 50 ohms on the transformer, but clearly lower. And it has not converged completely here at 1 Hz. It looks like maybe it will be minus 135 or something like that. I have added a Bootstrap circuit, an emitter follower that takes the source voltage from here, which follows the gate, and applies it to the drain. This means that the AC voltage between gate and drain is eliminated, and that makes the capacitance disappear, since there is no AC voltage across it. This increases the impedance in this point by removing the capacitive load. So I had to put about 3 pf from here to ground to keep the resonance at the same frequency. And the output impedance from the bipolar is much lower than the output impedance from the FET. So I have a very low impedance on the transformer here, and I make it about 50 ohms with this series resistor. Here is the phase noise with the Bootstrap circuit in place. This is what I had before without it, so it is a significant improvement at 1 Hz offset. And at even closer to the carrier, the improvement may be bigger, but I cannot see that. It would take far too much time, and I don't know whether my system is good enough to see that kind of noise. I am feeding the source follower through 3 kilo ohms and with the step-up transformer for 12 kilo ohms impedance on the gate. The effect of removing the gate-to-drain capacitance will be much larger when the source is the crystal filter, because small capacitance variations will have a much larger effect when they are parallel with the crystal. A very small capacitance will make a phase shift. And when it is only a resistor, the phase shift is much smaller. There is a much lower Q when the resonance is only from the transformer. Here is the phase noise that I see when sending the signal from the Wenzel oscillator through the crystal filter to the source follower. And I'm using the step-up transformer, so the impedance at the gate is 12 kilo ohms. And here is what I have when I was sending the signal through the 3 kilo ohm resistor, also using the step-up transformer to see 12 kilo ohms on the gate. And there is a significant difference. At 10 Hz offset through the crystal filter is better, but at 1 Hz offset it is a little bit worse. But the differences are fairly small, about 2 or 3 decibels. I have connected the crystal filter directly to the gate of the source follower. And here is what I see. And I can put the ruler here. And here is what I had when I connected it through the step-up transformer. So there is a significant improvement at the 1 Hz offset, but at 10 Hz offset the difference is the other way around. I don't know if it is really significant, because what is natural, the amplitude is down by 6 decibels. So I have lost not only 6 decibels, but more than 10. Now I don't know, because this is out of specifications for the test system. So I don't know if this is real or if it is an artifact that it is as low as 185. Probably not. But this is probably a more reasonable far range noise, minus 175. That is, it looks like a valid measurement because it's flat like this. Just out of curiosity, I have reduced the signal level by 6 decibels. And of course, as expected, the noise floor far from the carrier, the white noise floor, has been degraded by 6 decibels. What I had at full signal level is this, and the difference is very close to 6 decibels. But close to the carrier, there are subtle differences. Here is the reduced signal level, if I put the ruler like that, and here is what I had before. So there is some peak here. This value has been degraded significantly. Maybe it is the white noise floor from the amplifier that lifts by, is it 1.5 decibel? And here at 1 Hertz, more interesting, the difference is very small. Here the difference is not really very large, but we can see the shape of the curve is a little bit different. So there was nothing interesting I have detected. There could have been, I don't know, but this is the result I have. I decided this would be good enough for now. So I opened the box to fix the mechanics for making the box less sensitive to vibrations. Then I discovered something. There were oscillations at about 500 megahertz. Not very visible on the oscilloscope, which is limited much lower than that, but I could see it. So I added some capacitors and some other little things, and now I have this situation. so it is significantly better, and it has not even converged yet here. So this is indeed good enough. And what is interesting is if you look at the noise at 10 kilohertz, it's here now. When the oscillations were present, it was much higher. And as you may recall, when I changed from 12 kilo ohms to 3 kilo ohms, the noise should have gone up by 6 decibels, but it went up much more. And that was, of course, because the noise caused by these oscillations. Here is the proper comparison. Now with 3 kilo ohms at the gate, and here with 12 kilo ohms at the gate. And you can see here the difference is not very large at the flat noise floor. But it is significant here at 1 Hz offset. This is the schematic diagram I am using now. A couple of capacitors, and this ferrite bead stops oscillations at 500 MHz. And this resistor stops oscillations that can occur at about 70 MHz. It gives a load resistively on the source that makes the AC voltage on the drain just a little bit smaller than on the gate, but it's still pretty close, so this removal of the drain capacitor is almost perfect still. The output impedance of the bipolar is low and transformed to half the voltage. 4 times lower impedance is extremely low. So the output impedance is 47 ohms here. I have added a 90-degree phase shifter, inductor capacitor, and a resistor to ground. This gives a 90-degree phase shift, which is adjustable a little bit up and down. And the gain is 0. It's the same level here and here. And then an amplifier, which gives a gain of about 2, 11 to 5. And I'm testing this by sending the signal from the Wenzel oscillator as it is from a 50 ohm source impedance to this point, which means directly to the source follower. Here is the result. The marker here at 1 Hz offset says minus 136.6 dBc per Hertz. I had expected somewhat lower because I'm feeding from 50 ohms only. But I will go on with this. It is still below the 136 target. There will be some additional noise from the crystal, presumably. But measurements of these things take a long time, so I want this oscillator quicker rather than perfect. I will use the signal from the collector of the transistor to feed the power amplifier, and I added 1 extra turn on the transformer to get the suitable level to feed the limiter. And then the limiter is a resistor and a FET that I can control to attenuate a little. And the voltage controlling the FET comes from the PA input with a rectifier, full wave, and then a capacitor and a fairly large resistor feeding the base of the FET, making it a variable resistor. And this gives a constant signal level at the output. I am measuring the signal through a step-down transformer here, 4 to 2 turns, and a 47 ohm resistor to set the impedance to fit to the measurement system. And of course, the voltage divider for the channel voltage of the FET is not connected to the limiter output. That was a drawing error. Here is the performance as an oscillator. The frequency is now 0.03 Hz from the Wenzel oscillator. When I started measurement, it was at 0.18 approximately, and it has drifted since then. And now it is here. There is a signal, a spur from the difference between the reference and the signal under test. I will save this and then feed the Wenzel oscillator into the unit for the same signal level, and the frequency is approximately the same with good margin, close enough. I have disconnected feedback and connected the Wenzel oscillator to the input connector, and I'm still measuring at the measurement corrector. And now the signal level is 9.1 dBm, and the frequency offset is of course very small. What I had before is this, 9.1 or 9.0 dBm for the signal, and it's the same now. And the frequency was then 0.03, but now it is of course the Wenzel oscillator frequency. And if I start it, it looks like this. The lid is not on. I will place it on and then swap the outputs to measure the feedback output, which will operate exactly the same as in an oscillator, because the input is 50 ohms. And then I will look at the signal at the measurement output, and it will have a different level, but it is loaded by 50 ohms all the time, both outputs. The signal level at the feedback output is 6 decibels higher than the level at the measurement output, but both outputs see 50 ohms all the time. Here is the phase noise I see when sending the signal from the Wenzel oscillator through the selective amplifier at the same signal level that was present in the amplifier when it was running as an oscillator, giving this phase noise. And it's interesting to see that above about 10 Hz, the curves are identical. Somewhat more noise and spurs when it was an oscillator, but very similar. But at 1 Hz offset, there is a significant difference. This is because when it is an oscillator, there is positive feedback. At only 1 Hz offset, the gain through the amplifier is high, almost unity. On oscillation frequency it is 1.0 exactly, but 1 Hz off it is a little bit less, but still very large, and positive feedback increases gain. And it seems to be from minus 132, the marker says 132.2, to here minus 122. The marker is a little bit high, and it says 121.6. So there is a 10 dB extra gain because of feedback. Assuming, of course, that there is no noise produced by the crystal. Here I'm feeding the amplifier through a 3 kilo ohm resistor. And it's a bit noisy, but I can put the ruler like this. And here is the noise when I was feeding it through the crystal filter. And as you can see, around 1 Hz. It is more or less exactly the same to the accuracy I can get with this system. But at something like 3 Hz, there is more noise when I feed through the crystal filter. I think that is the noise from the Wenzel oscillator that is no longer eliminated by the trick having the same signal through the amplifier as for the reference on the PN2060. The white noise here with the crystal is lower than what I have with the 3 kilo ohm resistor. That is because the impedance of the crystal filter is significantly lower than 3 kilo ohms, well away from the center frequency. So that explains the difference, and it's visible all the way up to about 20 Hz or so. At 10 Hz, the phase noise is the same. But one interesting thing is that at 0.1 Hz, the noise looks significantly higher when the crystal is the source. But on the other hand, the signal has not converged, so this is uncertain. Anyway, the conclusion is, at 1 Hz I do not see any noise caused by the crystal itself. Everything is because of the noise of the amplifier. Now that I have found that the noise I see at 1 Hz offset is caused by the amplifier noise at 1 Hz at this level, it is interesting to consider whether it would be a good thing to make a lower impedance from the crystal filter. Here is 3 kilo ohms, and here is with 50 ohms, and it's significantly lower, something like 3 decibels. So rather than having 3 kilo ohms from the crystal filter, I could transform it downwards to 1/4 of that and not reach as low as this, but a little bit lower. That would degrade the noise at wide range by 6 decibels, and for the purpose I'm looking, it might not be harmful. On the other hand, I want to lower the frequency, means putting a bigger capacitor across the crystal. That will probably make the impedance lower. So I will not change anything, but start to look at what happens when I change the frequency. With 100 pf parallel to the crystals and about 40 pf for the coupling capacitor, I get this frequency response. It is now on the frequency of the shifted rubidium oscillator. The output impedance from the filter is only about 300 ohms, so I have added a transformer transforming the voltage 1 to 3, which gives about 3 kilo ohms into the amplifier. I have verified the frequency by coupling the rubidium oscillator shifted signal very loosely to the input. And as you can see, the frequency error is far below 1 Hz. The correct frequency is here, and the maximum is, well, maybe here. And I will need a capacitance diode and some other stuff to lock it to the rubidium, so I don't have any reason to do this more accurately. When I tried to make an oscillator, I found there were 2 frequencies present at the same time, the 10 MHz plus something much lower. So when I look at the response through the amplifier at 15 MHz span, I see a strong resonance at 3.74 megahertz. I found this is the 100 pf on the crystal plus stray capacitances in resonance with the inductance of the transformer, the small winding, which is only 3 turns. So I have to kill this resonance. I added a series link, 33 pf, 47 microhenry and 360 ohms, parallel to the input of the amplifier. That means parallel to the 3 turns of the transformer, which has 9 turns in total. And this has reduced the resonance to warp below where there could be a problem. When I look at 10 MHz, I don't see much influence of that series resonator at 3.7 MHz. Q is still 1,095,000. When I apply feedback and turn the unit into an oscillator, I see a very strong phase noise at 1 Hz. And in particular, the slope here is very steep. When I had it oscillating at the frequency of the vent cell, this was what I saw. So something is very wrong. Maybe I have placed the resonance far too close to the series resonance, or maybe the transformer is noisy. It is from 61 material, while the previous transformer was from 67 material. Otherwise, there are no changes and the signal level in the amplifier is as before. And I have not seen any parasitic oscillations. I made a new transformer on a 67 core, this time 4 plus 8 turns with a somewhat thinner wire compared to 3 plus 6 turns on the 61 core. This one is slightly capacitive, while the old one was slightly inductive. But performance is equally bad as before. So something is wrong with this idea, moving the frequency as much as this. I have disconnected the crystal filter and connected the vent cell oscillator to the amplifier through the transformer and through 270 ohm. Means that the transformer is fed by 320 ohms, which is close to the impedance of the crystal filter. And I've done this to verify that the noise is not caused by the amplifier. And this is the result at the main output. And it is below minus 135 dBc per hertz. There are still circles in the data points here, so it has not converged yet. And of course the result is a little bit questionable. I don't know exactly how far down I can trust the PN2060. The specification says minus 130, but that's for 90 minutes. I awaited far longer than that. Here is the phase noise at the feedback output. It's also about minus 135 dBc per hertz after about 500 averages, and it has not converged yet. So there is no problem with the amplitude limiter. The problem is with the crystal filter. Here is the frequency response. It looks perfectly okay, with the phase close to 0 at the peak. And when I look at the bandwidth, I find the Q is 1.11 million. So there's nothing wrong with the crystal filter as it comes to the frequency response. I have reconfigured the filter. Now I'm sending a current into it through a transformer. Q is the same, phase is 0 at the correct place, the frequency is about 1.5 Hz higher. Here is the old filter configuration. I had to put a large number of turns on the secondary here, and I was suspecting maybe that would cause a problem. So I made this new configuration where I make a current by transforming from 50 ohms by a factor of 4, means 16 times in impedance, feed it through the crystal to the output here. And this capacitor is very small, so it shouldn't be any problem at all. And of course there is a tuning capacitor here. It's about 140 pF. I have applied feedback again, and now the oscillator is running with a new filter configuration. And the noise is very high now also. So I must conclude that the crystals themselves are far more noisy when operating with a large capacitor very close to the series resonance frequency. Now I have gone to the other extreme. The tuning capacitor is only 22 pF. The frequency is much higher. It's about 30 Hz above the Wenzel oscillator now. Q is now about 1 million. It is a little bit lower than before, but the impedance is much higher. I have had to transform the impedance downwards to get the same level as I have had before. I'm still using the second version of the crystal filter with the transformer sending current into the crystal. Frequency is now about 70 Hz higher than before, and the phase noise looks normal. I will modify the frequency shifter for the rubidium oscillator to shift the frequency upwards instead of downwards, because the performance I see here looks similar to what I had when it was running at the Wenzel frequency, which is 35 Hz below this frequency. I have not checked the crystal current, and there are other things I have to check for optimization, but now it looks normal, and it is already converged at minus 121 approximately. Not particularly good, but not very bad as it was when I had it close to the series resonance frequency. I allowed the unit to run overnight. What I see is encouraging. The deviations from a straight line are very small. It probably continues well below 0.1 Hz offset from the carrier. There could be some steeper here because the straight line is pretty high. It should be something like this. But it's not bad compared to what I have had before, because I always had problems at 0.1 Hz. And now I know it's normal due to turbulent airflow inside the boxes. This box has no power amplifier, so it is not so sensitive. The oscillator is now running on a frequency close to my shifted rubidium source. The upper trace is the rubidium source. It contains a little bit on the frequency on the other side of the 10 MHz, but that will not make any difference because the PLL will not let anything through that is far from the carrier. And the lower trace is the oscillator. If I put my hand somewhere on it, you can see how it drifts. So now I will look at the phase noise. The frequency of my upshifted oscillator is 11.25 Hz above the Wenzel oscillator. And that's the frequency of my upshifted rubidium source. And the noise isn't quite as good as I had hoped for, but it's not bad anymore. If I put the ruler for 30 dB per decade. It's like this. So it goes a little bit steeper here at 0.1 up to 1 Hertz. But maybe it will go down if I would wait long enough. Anyway, I will do some different experiments, changing those things that I can change and see if it makes any difference. I have tried to change currents, voltages, and the transformation on the input to the source follower, and also coupling through a capacitor or through a transformer to inject voltage or current into the resonator. And all the time the best I have had is 120.5. Right now this measurement shows minus 119.5 at 1 Hertz. I have seen an improvement here when changing the operating position of the bipolar transistors, but at 1 Hertz offset it's always the same, with small changes, and a few times a significant degradation down to maybe 115. The measurement time is about 20 hours for this, and I can see it is a good straight line down to 0.1 Hertz. 0.01 Hertz. It has not converged, but there are no circles here, so the result is about 47 dBc per Hertz at 0.01 Hertz. And I can see the curvature when coming very close to the carrier. I have been running Linrad in parallel with the same data, and I can see that at 1 Hertz offset here is 119.5 also. The measurements give the same result. But here in Linrad I can see some interesting things. The green trace is the sum of the phase noise of the Wenzel oscillator and my test object. And the test object is the yellow. And the red is my channel 2 reference oscillator, which is better than the Wenzel at 1 Hertz offset. But at 0.1 Hertz offset, the Wenzel is significantly better than my reference oscillator. And this is interesting information because I wanted to optimize my test system for measurements on the multicrystal oscillator, which I want to study down to 0.1 Hertz and improving by 3 decibels or more actually, because the green points are very close to the yellow line. This means that the Wenzel is significantly better than my current experimental oscillator. The difference is only 1 decibel. When the difference is 3 decibels, the noise is the same from both oscillators. It's like here at 0.2 Hertz or 0.25 Hertz, there is about 3 decibels to both oscillators. It means all 3 oscillators have the same noise level at this frequency offset, and that common noise level is minus 99 dBc per Hertz. And the curvature here is noise from the Schottky diode mixers, I think, and they may be different for the 2 channels, so I'm not sure that the Wenzel really is more noisy than my channel 2 oscillators. In Linrad I can look at the amplitude noise, which is here, and which is much lower than the phase noise. And you can see down here that the red dots are below the white trace, only very close to the carrier. But the white trace, that is the AM noise, and it is very low, minus 120 dBc per hertz at 0.1 hertz offset. So the limiter is okay, and the amplifier does not add amplitude noise modulation. And the conclusion, I think, is that the phase noise I see comes from the crystals. And I had expected much lower, because there are 4 crystals in parallel in this box. I have been running a second instance of Linrad at the same time. Here I can see the noise at 1 Hz offset is minus 119.5, where the mouse is now. And that's the same as I had with the PN2060. It says minus 119.5 at 1 Hz offset. If I set linear scale and compress it properly, like this, I can see the noise at 100 Hz offset. That's here. And it looks like something minus 169 or so. It's a little above minus 170, but it hasn't converged properly. And all the lines we see, they are overtones in the audio spectrum of the difference frequency between the reference oscillator and the signal oscillator. And I can check the PN2060, 100 Hz. It says a little above minus 170. So the different methods of measuring this agree. And that's nice. Here is phase noise and amplitude noise in the same graph. And you can see the phase noise here is far above the amplitude noise. And up here you see the correlation, and it is 0. So the small level of the amplitude noise is uncorrelated to the phase noise. And only at the beginning I really have the amplitude noise. Then it is just a measurement uncertainty, because the time is not long enough. Here one can see only the first part from where it starts up to about 0.3 Hz. There is a significant signal for the amplitude noise. Then the amplitude noise is on the same level as the imaginary part, which means that the signal to noise ratio is far too bad for the correlation to be relevant. I have tried different temperatures for the crystals, from 87.8 down to 73, with the thermometer properly coupled to the oven. This value, approximately 65, was the original setting I had, and that was for the crystal from Bell Labs, which gave at best minus 121 dBc per Hertz at a frequency of 11.25 Hertz. That's the offset from the Wenzel oscillator. Now I find, changing nothing but the temperature, that there is an optimum around 79 degrees. After finding this, I have tried to replace the 4 crystals by another group of 4 crystals. I created a noise burst now. You can see the strong signal here, so the result will be degraded pretty soon, or already maybe it has been. I I think I saw minus 123.0 in the PN2060, as well as in Linrod at 1 Hz, which is here. It says 122.7 at the moment, but I think I have destroyed a little bit by being careless when I put the camera in place in front of the computer. There are interesting things. At 0.1 Hz I see minus 90, but well, this was very different not long ago, with the green trace very close to the yellow trace. Anyway, the temperature now is 80.2 degrees. I have restarted Linrod and also the PN2060. It has been running now for 6 hours and 25 minutes. And the noise at 1 Hz offset in PN2060 is 122.8. And if I look in Linrod, minus 124 is this line, and 1 Hz. So it says minus 123 at this point. And at 1 Hz I know that the Wenzel is at minus 120. And that's here. The green trace is a little bit above that. Looks like 1.5 decibel. If I try to make a smooth line here. Above the yellow trace, which is at minus 122 point something. So that seems to fit reasonably well. And it means that the oscillator is about 3 decibels better than the Wenzel. And my channel 2 oscillator is significantly better than the Wenzel oscillator. Actually, it is only 2 decibels above this yellow trace, so it is probably just a little better than minus 123. But at 0.1 Hz, the channel 2 oscillator is not good at all, and even closer to the carrier it drifts away and becomes 6 decibels more noisy than the Wenzel oscillator, which is 3 decibels above the yellow trace, means the level is the same for the Wenzel and for the box I'm experimenting with, and the level is at 0.07 Hertz minus 88 dBc per Hertz. I had this other instance of Linrod running in parallel, and at 1 Hertz it looks like minus 123 or maybe 122.8. With the current test, the 4 crystals, 122.8. The Wenzel oscillator is at minus 120, but I read minus 118.3 or so, because that's the sum of the noise, minus 122.8 and 120 becomes minus 118 point something. I'm not doing the math properly, but it's that sort of, it seems to fit pretty well. I have increased the temperature by 2.5 degrees to 82.7 degrees. The phase noise now at 1 Hz reads 122.6, and that's not a significant difference from the previous result. And it's the same here, of course. At 0.1 Hz now it is minus 91 point some very little. Looking for the phase noise at 1 Hz offset is a very slow process. I have to wait about 6 hours to get a reasonably stable value. I don't know exactly what the error is, but several tenths of a decibel. And then when comparing two different values, the total uncertainty becomes unacceptably large. So what I can do in Linrad is to set the linear mode for displaying the phase noise, and then I select the suitable X gain, 7 in this case, that limits the range to 2.6 Hz, and it starts at 0.67 or something like that. The starting point is given by the Fourier transform size, which is in this case 16. And I can start collecting the phase noise by clicking on the signal here. And it takes a little while. And then you can see I didn't click at the right frequency because the signal came here. Now Linrad has an automatic frequency control, so it will come at the proper frequency pretty soon. Like that. And then the phase noise will start to appear in the phase noise window here. The first value is not right because that had the frequency jump, so I will skip the first couple of transforms. And here comes the phase noise. Now, Linrad is computing the average of the results over the green range here. And that comes here as minus 130 right now. But I also have the results in the, I don't know what it's called, the other window associated to Linrad. And you can see how the value scatters from 127 up to 130.5. Now I will wait for a while to allow this to stabilize, and I will look afterwards how many transforms I need to get a reasonably stable value. So I start to make a recording with time-lapse. Here is the time-lapse video. It starts as I showed in the previous section, and I step forward 1 frame at a time and look at this average value. And it rapidly goes down to about 128. So I go back and look at the spectrum, and here you can see there are blue regions. That's when the value is negative. Those are not included in the average. And now it has gone down to minus 128. And now I play it it is 30 frames per second when I play it, but recording was 1 frame every 10 seconds. And now 128.6 after 300 transforms. That's about so 300 transforms, that's enough. Then there was an event. It's now 128.4 only. And now the result is going down. And here you can see why. It is going down to 127 point something. And here is a noise burst. And here is one more. And they come more frequently now. Yet one more. And stronger and longer time. These noise bursts are typically caused by poor connections in the B and C connectors. So I have cleaned the connectors carefully and also bent the contact fingers a bit to increase the contact pressure. And now it is better. I look like this. And you see, the value is a little bit better, 128.9, and I allow it to run. And it stays. And it stays until I stop this recording at 1800 something. Here is another kind of instability. I'm looking in the Allen graph and in the frequency versus time window. You can see that the Wenzel oscillator, the green trace, is more stable than my other oscillator, the red trace. But at this point, there is a frequency jump that is the same in both channels, means it comes from my oscillator under test. Now, this isn't really harmful for the intended use because it will come in only one channel, and if it occurs seldomly enough, it will not matter. Because it's not in the other channel, so it will not give a correlation result. 3 times 10 to minus 13 is not bad for the Allen deviation at 1 Hz offset. The yellow result is the correlation between the two curves. And it is slightly better than each one separately. And frequency versus time. There is correlated noise, but not very significant. The frequency drift will be corrected by locking it to the rubidium oscillator. The box is sitting like this and it changes the frequency as the room temperature changes. Since frequency drift is a major issue here, I can look at the Hadamard deviation. And it's a little bit better at 1 Hz, 1.77 times 10 to minus 13 for the correlated part. The average noise, which I see here, has been unstable. It was hovering around minus 128, but there were occasional events here So I decided this must be caused by the crystals. And then I thought maybe if I try to force them to age faster by increasing the power. I increased the current from nominal 1 milliamp to 2 milliamps, and that increased the average noise significantly, went down to minus 125. But then it improved after a while, a little bit. And now I have reduced the power in the crystals. The current is currently 0.77 milliamps, and now it seems stable and better. And when I look at the PN2060, it looks like minus 125. And the readout says minus 124.9. So this has improved the situation significantly. And here is the Allen graph. At 1 second, it says 3.6 times 10 to minus 13. And I look at the Hadamard graph here, which is very much better. At 1 second, 8.9 times 10 to minus 14. Looking at frequency versus time, we don't see much correlated noise, and this is with half a second per pixel. So it is the very slow things. And you can see clearly that the red trace is more noisy than the green, although the difference is not as large as I occasionally have seen it. But you can see here, in 10 seconds, there is a significantly more noisy signal from channel 2. And this is the Hadamard graph. If I look at the Allen, there is not any difference, because the slope here, the steady increase in the frequency, it is 0.1 millihertz per division. So it is small changes, but significant. I have reduced the crystal current to 0.55 milliamps, and this has degraded the phase noise, as I see here. And here was an event, and that contributes to the degraded average phase noise. The PN2060 tells me minus 123 dBc per hertz at 1 hertz offset. And before that interference event, it was a little better, but still significantly degraded compared with the slightly higher crystal current. It is the current for each crystal. The total current is 4 times larger because I have 4 crystals. Frequency versus time has a funny behavior. I think the green trace, that is the frequency change of my oscillator under test. The fact that the separation between the green and the red makes this event here means that the effect of changing temperature is slower on the channel 2 oscillator than on my unit under test. I have set the crystal current to 0.88 milliamps. That gives about 1 decibel more power through the crystals than I had with 0.77 milliamps. And the average phase noise now is minus 113.17. I had minus 130.23. So there is no significant difference. The phase noise at 1 hertz, according to Linrod, is minus 124 dBc per hertz. The Allen deviation at 1 second is 1.7 times 10 to minus 13. And frequency versus time looks like this. So it is more relevant to look at the Hadamard deviation, which is very low. I can change this. And it looks like this. At 1 second, 9.3 times 10 to minus 14. At an offset of 1 Hertz, the PN2060 gives minus 125 dBc per Hertz. The table says minus 125.3, but the decimal is of course not particularly accurate. And the slope is nicely f to minus 3, 30 decibels per decade. And it's a straight line all the way up to 0.1 Hertz offset. Now my oscillator has returned to its noisy state again, with an average noise at minus 125. That's what I had before I made this experiment, running it at high power. And the phase noise is only minus 120. And of course I see the same in the PN2060, minus 119.8. This event happened while nobody was in the room. And it is calm outside and there's no physical vibrations or things that can have happened to the unit. It is not particularly good right now. You can see the noisiness. There is correlated noise here. So performance is degraded for some unknown reason. But this particular event, very odd. Maybe it is the crystals that misbehave, or it could be something else that is drifting for whatever reason, aging or something. I hit the unit with a hammer and now it is really noisy. I have reduced the scale and I still cannot see the signal, so I move it and I cannot see it now. I have to wait. The noise level is extremely high. You can see here the white region is 10 Hertz wide now. And it's of course visible down here. Correlated noise on both sides, all the way out here. And the frequency jump is large. Here, with the very high scale number 5, I can see the jump here, which is about 200 millihertz, 0.2 hertz. The average noise has declined by about 3 decibels. It was minus 130 at best. The phase noise at 1 hertz offset is now minus 121.4 in Linrad. I have had the PN2060 running and it indicates 121.8 for the position of the marker, and it sits properly on the line, I think. The Allen deviation is about 2.2 times 10 to minus 13 at 1 second, and about 2 times 10 to minus 12 at 10 seconds. And the Hadamard deviation is flat at about 10 to minus 13 from 0.3 seconds all the way up to 2, 3, 4 seconds, and then it increases. And looking at frequency versus time, we can clearly see the correlated noise between the two channels. And the noise is much stronger than the noise in one or the other reference oscillator. But this is very slow. It is 5 seconds for each pixel. I spent quite some time trying to get back the performance for average noise at -130. But I failed, and I don't want to continue to rebuild everything, because performance is not bad even at this level. I want to continue, for the main purpose of this video, to get 2 reference oscillators, both of them locked to the shifted rubidium source. Now there is a new problem. I have, you can see, interferences coming now and then. They are caused by something wrong in channel 1. Here it comes. And since I see something here at the center, it means that this is an amplitude interference. So when doing the changes I did now, because I have phase locked my oscillator to the shifted rubidium source, and then I can see frequency versus time. It doesn't look particularly nice, but I will wait for some time, because I guess this will now show the stability of the Wenzel oscillator, the long time stability. And the short time fluctuations, whether they come from a too short time constant in the PLL, or whether they are from my oscillator, I don't know. But I will find out. These amplitude problems in channel 1 do not affect the frequency determination, so I will not try to fix it right now. It seems that the interference is equally strong on the mirror image as on the main signal, and that indicates that the problem is in the signal path and not in the oscillator path. It's obvious that the green trace is very flat. It has gone from here 0.5 millihertz to here, which is 0.3 millihertz. So 0.1 millihertz in, 6,000 seconds. And now the phase noise is not good at all, but that doesn't matter for this long time measurement. I have increased the PLL time constant by a factor of 20. And it will take some time before it has stabilized, but it looks much calmer here. And when I look at the phase noise, it is now much better. It is probably becoming a little better than -120. With a PLL time constant, like you see here, this soft curve, this noise that I see on the Wenzel is the noise from my 4-crystal oscillator. And I can try to make the time constant even bigger than this, and then will probably the low frequency oscillations grow, because the instabilities of my 4-crystal oscillator will not be corrected fast enough by the frequency shifted rubidium source. Now, I want it to be uncorrelated to the rubidium source, because I want to have two channels that are uncorrelated up to fairly long times, because I'm going to use correlation to dig for instabilities below the instability of these oscillators and the rubidium source. Now the time constant is another factor of 10 slower, and the green trace is much calmer, while the red is clearly much more noisy than the green. And I knew that my channel 2 oscillator is much more noisy, very close to the carrier. And here there is a small frequency jump downwards and then upwards, and it is present in the red trace also, which means it comes from my 4-crystal oscillator. It made some jump, and also here, so I don't know the reason for that, and I don't see it here. This looks calm. But the phase noise at 1 Hz is not particularly good. And of course that frequency jump produces noise at 1 Hz offset. This has been running for about 7 hours now. The frequency has drifted from about, if I remember correctly, 0.4 millihertz to minus 1.4. So the Wenzel has drifted 1 millihertz, if I assume that the rubidium oscillator is more stable than that. And then I can see here, these oscillations are due to my 4-crystal oscillator. So I should use a slightly shorter time constant than this, what I have used now, for optimum performance. And you can see the correlated noise of very long times, 500 seconds. Well, from here to here it's almost 1000 seconds. I can look at the Allen deviation. It looks like this. 1 second, 2 times 10 to minus 13. There is a difference between the green and the red dots, but here they become equal. That is 1000 seconds. So that is the time constant. Well, it's related to the time constant of the phase lock loop. And above 1000 seconds, what I see is determined entirely by the rubidium oscillator. And it is clear that the channel 2 oscillator is more noisy than the channel 1 on all time scales. And the difference is about a factor of 2. And the phase noise here is minus 120 dBc per Hertz at 1 Hertz offset. This seems to be an optimum time constant for the phase locking to the rubidium source. The green trace, the frequency versus time for the Wenzel oscillator, it is a combination of the noise from my 4-crystal oscillator and the Wenzel oscillator. The red trace is my channel 2 oscillator, which is phase locked to the Wenzel. And it looks like I have a too long time constant there. I will reduce it, I think, by a factor of 4 could be reasonable. This time the phase noise at 1 Hertz offset is minus 122 dBc per Hertz. So I guess the previous time there was some noise event. This looks okay now. The green and the red trace follow each other reasonably well. I don't see any overshoots because of too long time constants. The phase noise is 122 dBc per hertz. The separation between green and red points is, I can look here, it's from 8.6 up to 1.09, and that is at 1000 seconds. So it means the channel 1 and the channel 2 oscillators are uncorrelated up to about 1000 seconds. So at 100 seconds they are completely uncorrelated, although the average frequency is well locked. The Allen deviation at 1 second is 2.2 times 10 to minus 13. That is the correlated component, while the two channels are 2.6 and 3.0 respectively. This will be good enough for now. I will use this phase-locked oscillator with the time constant that I have now as my reference oscillator in the future. And then I will make one more to lock also to the shifted. I have connected a second rubidium source to measure it with my phase noise measurement system. Here is the result, and you can see the close range phase noise as a scatter of the points, but the green trace is very stable now, and that is the Wenzel oscillator. And here is my 4 crystal oscillator phase locked to the other rubidium source, which is frequency shifted by about 20 Hz. And when I started the rubidium source, there was some initial frequency drift when it was warming up, but then it is very stable. And it is clear that the instability of the channel 2 oscillator is similar to what I have seen here, but it's more difficult to see it since the track is so wide. And when looking with the PN2060, it doesn't look very interesting. At 0.1 Hz, the noise is minus 62 dBc per Hertz. So one has to go much closer to the carrier to see the merits of the rubidium source. I have restarted measurement of the rubidium source using my old oscillators. Green trace is the Wenzel oscillator, and red trace is my homemade oscillator, which is phase locked to the Wenzel. And then when I look at the Allen deviation, I see that the Wenzel oscillator at 100 seconds is 10 to minus 12. And I think at 100 seconds the noise of the rubidium source is no longer significant. Close to the carrier, the noise level is very high. You can see here the waterfall is completely white. That is this region. 1 second, that is 1 Hertz offset. That is very close here. And we see at something like 300 seconds, the separation between red and green starts to decrease. It means that, well, up to 300 seconds the oscillators are independent. And then at 3000 seconds the phase locking is completely done. So the red trace over long times is going up and down around the green trace. Here is the circuit diagram of the oscillator. The way to tune it is first to set this capacitor for the Q of the crystal to degrade just a little from 1.1 million down to 1.07 million or something like that. Then this transformer is to get a good stop band attenuation. So the first step is to set the number of turns to get something in neighborhood of the right number ratio. And then one can fine-tune with this capacitor for a perfect symmetric response and very good suppression outside the frequency of resonance. This resistor is to guarantee 0 voltage across the crystal, because at this point there is a bias for the FET. This is the type number of this ferrite I have used, and putting the wire through like that, so it goes through 3 of the holes. The source follower with its bootstrap arrangement from this bipolar transistor following it. Then there is an amplifier with 2 transistors in parallel, because I'm loading it quite heavily with this 47 ohm resistor to the feedback output. And then there is this FET which rectifies the RF from this output, and it lifts the gate above this bias voltage, and that reduces the signal level. So this is the amplitude limiter. And then this output also from the drain, it goes to the output buffer stage. And this is also 2 transistors in parallel. I forgot to show that in the diagram. And then the output here with a 47 ohm resistor and 1 nanofarad in series to get a 50 ohm output impedance. So these are the components that are doubled. The transistors have independent bias voltages because the noise generated by the resistors should be uncorrelated for the 2 transistors. So that was an old thing from long ago. I didn't change it because it does no harm, but I don't think it is necessary. Here is what the unit looks like internally. It may be hard to see, but it's not very nice, the layout. It just happened to become like this when I gradually added components. And here is a closer look. The phase locking input with the control diodes. The crystals are inside this compartment. And the stop band transformer. And then it's hard to see, but the JFET and its accompanying bipolar for the Bootstrap. And then there is a lot of space for next amplifier, and this is the output amplifier, and it's the remainders of the old output amplifier I had here, and the limiter. Here is another old oscillator which I now have modified to be similar to the one you just saw the schematic diagram from. And here is the phase noise. At 1 Hz here it says minus 124 dBc per Hertz. So this is quite okay. All this stuff here is because the frequency is very close to the frequency of the Wenzel oscillator. The difference is at this moment 0.18 Hz only. So we get a spur at 0.18 Hz. It was 0.1 Hz and it has drifted a little bit. And the overtones of that spur frequency and here, and it almost comes up to interfere with the result at 1 Hz offset. The structure here is an oscillation in the electronics of the oven. When I restart, it looks like this. It comes immediately. And now I switch off the supply voltage for the thermostat and restart again. And the problem is no longer there. So something is oscillating, I have to fix that. Here is what it looks like inside. There is no PLL input yet. We'll come from here. And here the layout is much cleaner because I knew in advance what I wanted. And up to this point, this is the schematic diagram that you just have seen. And then I'm using the old limiter, which is 2 crossed diodes here between 2 series resonant links. And this is the old output amplifier, which I'm not using. I'm taking the signal directly from the amplifier stage that feeds the limiter, and then a transformer to not load it too much, just to measure the first steps. The oven is no longer oscillating, so I have a flat noise floor here. And the noise at 1 Hz offset looks like minus 124. And that's what I read here, 124.1. Although the trace is a little bit below the marker. So maybe 125. What I had before I fixed the thermostat oven is this. And you can see that in the region 10 Hz to 100 Hz there is an improvement. This is the old. This is what I have now. There are spurs here because I have shifted the frequency. So it is now 7 Hz above my reference oscillators. So I have spurs at 7 Hz, 14 Hz and 21 Hz should be. I have been running Linrad in parallel and I'm computing the average noise from 0.68 up to 2.6 exactly as I did before in this video. And now the average is minus 130.5. So it is significantly better than I had from the other oscillator. And I can read the sideband noise at 1 Hz. Here it reads minus 125 dBc per Hertz. And it's interesting to see that my reference oscillator number 2 plus the noise of this oscillator I'm testing is at minus 122. That is a difference of 3 decibels, which means that the reference oscillator in my channel 2 is equally good as the oscillator under test at -125, while the Wenzel oscillator reads -119, and I know from old measurements that it is -120. So it is the sum of the noise -125 plus the noise at 120 comes out as -119. Close to the carrier, here 0.1 Hertz. It is clear that the channel 2 oscillator is much noisier than the one in channel 1. The difference is about 6 decibels, and that makes the convergency slow for computation of the noise of the investigated unit. It looks like -90 if I try to estimate where the straight line is. And it's clear that the channel 2 oscillator has some phenomenon creating noise close to the carrier, and it is better than the Wenzel oscillator above 0.3 Hertz offset. And the difference is significant, about 4 decibels at 2 Hertz offset. And the same is of course valid for the PN2060. The gray trace here is very close to the green trace, means uncertainty is large. And the result is -88. So it is in agreement, but they are running on the same data, so, well, I don't know. But this is actually the main reason why I'm doing this video. I want better performance on my test system at close spacing at 0.1 Hertz from the carrier. The amplitude noise at 0.1 Hertz offset is significant, -108, far below the phase noise, but very close to the amplitude noise of the channel 1. So channel 1 AM noise is not as strong as it looks because it has a contribution from the signal under test. I don't know whether this is meaningful, but it's interesting to note. I have removed the amplitude limiter with 2 crossed diodes and replaced it with a gain control using a FET. This has improved the average noise by about 1 decibel. And when I look here, Linrad tells me the noise at 1 Hertz offset is -125.5 dBc per Hertz. And the PN2060 has been running simultaneously, and it shows me -125.8. And if I look at the curve, maybe it is a little better than that if I try to put a straight line through the noise. At 0.1 Hertz, I see something like 97 decibels, but there are circles in the traces, so they have not converged yet. The amplitude noise is much lower. It is at the same level as the imaginary port, and that is at -126 dBc per Hertz at 0.1 Hertz. And the separation between the two channels is significant here, which it was not before when the signal from the oscillator was far more noisy. I have changed the current through the crystals from 1.41 milliamps to 1.06 milliamps. That means that the power for each crystal is reduced from 140 microwatts to 78 microwatts. And this has caused a loss of 0.2 decibels on the average noise. Not very significant, but with these long waiting times, I think the value is fairly accurate. I will change to a current of 1.2 milliamp per crystal to get 100 microwatts power in each one. The resistance is about 70 ohms. And I think the performance will be somewhere in between. The phase noise shown by the PM2060 this time at 1 Hertz. It looks very good. It says minus 125.7. But it varies from time to time. You see the track is fairly noisy. With a lower power in the crystals, the noise in the flat noise floor is degraded. This is what I have now, and this is with about 2 decibels more power. And I can look here. There are no significant differences. Now the 2 oscillators with 4 crystals in each one are the reference oscillators for my Linrod system. Both of them are phase locked to the frequency shifted rubidium source, and the signal source is another rubidium source. And the frequency versus time, it has a drift. When it started, those traces were at 0, the latest 5,800 seconds, that's 1.5 hours, I think, is what you see in the graph. And the noisiness is very different from the 2 oscillators. I don't know the source, maybe the power supply are not very good on them, and it doesn't really matter because these are slow variations, 5 seconds per point, so I'm interested in frequency changes over ranges up to 2 points. You can see the Allen deviation. The yellow trace is the correlated, which is the measure of the device under test, that is the rubidium source. It comes out as 2 times 10 to minus 12 at 100 seconds, 2.24. And that is reasonable for rubidium sources. This is helpful when setting the frequencies correct for the phase locking. The lock range is small, so it has to be set reasonably accurately. The upper trace is the oscillator in channel number 1. The lower trace is the oscillator in channel number 2. And the trace at the center, which I am using to trigger the oscilloscope, that is the frequency shifted rubidium source. And these are the voltages of the PLL for both. The range is from 0 up to 5 volts. So 1.7 is a reasonable level. And it goes up and down, as you can see. And that is in order to keep track with the noise that is in the oscillators. I'm running the PM2060 in parallel, but I'm not using the same sources. In channel 1 I'm using the Wenzel oscillator, and in channel 2 I have one of the phase-locked oscillator, the one that is channel 2 in Linrod also. And the rubidium oscillator is pretty noisy. Here is the table. Minus 62 at 0.1 Hertz, minus 81 at 1 Hertz, minus 98 at 10 Hertz. And then it's so noisy, it's not interesting really. And here is the phase noise as seen by lean rod. At 0.1 Hertz it is minus 62, and 1 Hertz it is minus 80.7 or so. Now my multi-crystal oscillator with 21 crystals in parallel is the device under test. At 1 Hertz offset, the phase noise is about minus 131 dBc per Hertz. Maybe 130, maybe a little more. It takes a long time to get an accurate result from the PN2060. Leanrod has been running in parallel. The total time is 7 hours and 46 minutes. And the result from Leanrod is different. It says minus 129.4. I don't know the reason. Usually the same results are obtained from PN2060 and Leanrod. Here is another instance of Leanrod that has also been running in parallel, and it shows that the noise is 129.5, probably a little worse than minus 130. Here statistics is not as good, because this goes to much lower frequencies. I see minus 93 at 0.1 Hertz. Here is another instance of Leanrod that has also been running in parallel, and it shows that the noise is 129.5, probably a little worse than minus 130. Here statistics is not as good, because this goes to much lower frequencies. I see minus 93 at 0.1 Hertz. And the PN2060 at 0.1 Hertz shows minus 99 or so. Maybe the time constant is not long enough for the phase locking to the rubidium source. I will increase that to see if the difference between the measurement systems becomes smaller. And here is frequency versus time. Something happened at this point in time. That is 5,000 seconds ago. That is 1 hour and 20 minutes ago, and precisely at that time I opened the front door of my house to receive something and let in some outdoor cold air. And it's another room, but air moves around inside the house. So the electronics components inside the box change with temperature. Although the temperature in the crystal oven is probably fairly constant, the temperature of other things is not when the temperature in the room is changing. Now it's clear what the problem is. The noise of channel 1 has increased drastically, and now I read minus 128.5 for the phase noise, and it's fairly noisy here. And when I look at the spectrum, you can see here that the green trace is about 10 decibels stronger than the red. I have set Leanrod to show the phase noise of channel 1 in the baseband waterfall, because I suspect that the noise could come from the crystals. So now I will disconnect the power supply to the thermostat to see what happens when the temperature is changing on the crystals. Now the frequency has changed by about 10 Hz, and the phase noise in channel 1 is still unaffected. You can see the noise up here and also here. I will shift the frequency to the other side of the frequency scale in the baseband. The frequency has drifted by about 70 Hz now, and the phase noise of channel 1 is unaffected. It is still as strong as before. But it is not easy to see in the waterfall because the frequency is drifting too fast for the waterfall parameters I have set. But it will slow down eventually. I have changed the color scale, and I think it's easier to see now. This is the width of the noise, and if I look here, it is clearly narrower, although it's not easy to see, and this experiment didn't work out well. I have changed parameters and connected the crystal oven again. Here is the phase noise when the oven was cold, and here when it is warm. And I don't think there is any real difference. Now, when the thermostat is back at the normal temperature, and I go back to look at both channels and for the phase noise, it looks perfectly normal. This is only 5 minutes, and the average noise here somewhere minus 130. I wait for a while, but when I see here it looks normal also. The temperature cycling of the crystals seems to have solved the problem. Now at 1 Hz, it's here, a little bit better than minus 132 dBc per Hertz. And that's really good. It is obtained, this result, after 1 hour and 20 minutes. And statistics is not good enough to get the decimal on the phase noise. About 132. The result in the PN 2060 is a little better than minus 130, but there are circles around here, so when it has converged it will be a little bit better than this, maybe 132 or 133 even. And the higher resolution, going closer to the carrier, here I see at 1 Hz, about this level, that's minus 132. And at 0.1 Hz, it looks like minus 98. But here, the channel 1 noise is fairly high. It is about something from 78 to 90. That is 12 decibels. And that is easily seen here in the spectrum. This is about 10 decibels. And it's always stronger. And you can see also in the waterfall. So there is something which is not so good with the channel 1 oscillator at very short distances to the carrier. And here is frequency versus time. You can see the long time it takes for the two oscillators to reach the same frequency because of the very long time constant for the PLL. I will allow this to run for a long time now, looking for the stability of the average phase noise. There could be noise bursts from the channel 1 oscillator, I don't know that yet. So I will make a time-lapse video so I can check afterwards whether there have been any events. It seems that temperature cycling the crystals has removed the noise problem. Now I see minus 132 dBc per Hertz in this instance of Linrad, which goes down to 0.8 Hertz. The average from 0.8 up to 2.6 is minus 138.37 after 5,600 averages. So this looks like expected. The PN2060 has been running in parallel, and minus 132 looks like a good estimate of the average around here, even though the marker says minus 147, but that is just a statistical problem. At 0.1 Hertz, the result is minus 98.6 according to the numerical table. The close range measurement at 1 Hertz here is also minus 132, but at 0.1 Hertz the statistics is not good enough because channel 1 is rather noisy, as you can see here. It's about 82, while it is 92 in channel 2. So the distance from the bad channel down to the device under test is too big for the imaginary part to become 10 dB below. And also here at 1 Hertz, the separation from here to the red dots is not really good enough for an accurate reading, and we can see that by the statistical uncertainty. It is a little bit better here at 0.5 Hertz, but still it takes a long time. This has been running all those different screens for 10 hours. Here I have changed the orientation of the reference oscillator in channel 1, and it makes a big difference at a separation of about 0.75 Hertz. And I can see that also here. The difference between channel 1 and channel 2 was before about 10 decibels. Now it is about 4 decibels, which means that convergence will be much faster for the device under test, the correlated phase noise spectrum. The channel 1 oscillator is now beneath this textile thing, handkerchief I think it's called, and it's standing on the side now, which changes the flow of air inside. So the problem is turbulent airflow, and I have seen that before, as you can see in some earlier video. The PN2060 has been running for about 30 hours now, and the noise indicated looks something like minus 132 dBc per Hertz. It's hard to see, this is so noisy. I have magnified the region around 1 Hertz offset, and I can measure the separation between the scale lines like this. And this turns out to be 58 millimeters. And I placed a ruler where I think maybe a proper straight line would be. And then I can measure this. And that turns out to be 12.8 millimeters. The result I find is then 2.2 decibels. So what I read is minus 132.2, and with some inaccuracy, maybe plus minus 1 millimeter or so. The Linrod screen after 18 hours gives me at 1 Hz offset 132.0. The noise in the signal is low, the imaginary part is all the way down here, and the signal is almost a smooth curve. At 2 Hz, the noise is significant, but the signal-to-noise ratio here is not at all as good. The imaginary part is closer. That is a bit hard to see, but if I check the distance between the uncorrelated, it's here, and here it is about 3 decibels worse. And that means that the correlation has to do much more of the work to retrieve the signal, so it becomes more noisy, and even much more noisy up here, where this distance is even larger. This instance of Linrod also gives minus 132 at 1 Hz offset, that's here, and at 0.1 it gives minus 96. That is significantly worse than the value indicated by the PN2060, which is minus 100 here. But I have not yet fixed the time constant of the oscillators, so I will do that, make them longer. The Allen deviation is a nice, almost straight line. The curvature is small. A straight line from here will go something like this. And above 200 seconds, there is no difference between the noise in the two channels. And I can see that they go to the same value near 100 Hz. And obviously at 10 seconds, they are still a little bit correlated with the noise from the rubidium source. I had some problems trying to make the time constant longer, so I did some modifications, and that made the time constant actually a little bit faster. So I need something like 4 times more time constant. I will try to see if that will give a stable locking. Frequency versus time looks very good here. The scale is 0.02 here, and the curves follow each other nicely. And the big bending here is because now it's early morning and the sun has just started to reach into this room and it's warming up slowly. This is the loop filter for the PLL of the 2 reference oscillators. I have changed the resistor from 10 kilo ohms to 44 kilo ohms. That's a factor of 4. Means R times C is increased from 50 seconds to 225 seconds. That should reduce the amplitude of the noise modulation by a factor of 4.4 in amplitude, or 19 times in power. That's 13 decibels. But this change made no difference at all. I have changed the size of the Fourier transform that computes the phase noise, and that made a difference. Now I see 98 at 0.1 Hertz offset, but the statistics is very poor because with this large transform, measurement becomes very slow. This is only 700 transforms. And you can see that the imaginary part, the red dots, are only 4 decibels below the yellow trace. So if I try to make a straight line here, it is compatible with 100 dB for the noise at 0.1 Hertz. I have been running this time also the PN2060 in parallel for the same time, and it shows a little bit worse than minus 100 dB, but minus 100 is reasonably correct. The value at 1 Hertz offset looks like before, but it's very noisy. But when I look at Linrad, which is less noisy, it is faster, it looks now like minus 133 dBc per Hertz. This is because I had a problem with noise bursts from the device under test, and the performance degraded to something like minus 128, and I could clearly see noise bursts in the waterfall here. With the experience of temperature cycling crystals in another oscillator earlier in this video, I decided this is an aging problem, probably, so I switched the supply voltage on and off for a couple of times, maybe 10 times, and then started again, and the performance was clearly and significantly better than before. Well, 133 was a bit optimistic. It is more like 132.5. But I could see clearly an improvement here on the average noise. I have connected this unit. It switches the power on-off with a couple of seconds between on and off. On the Linrad screen it looks like this with the speed that I use for the baseband graph in the Allen variation measurement. And I will disconnect the thermostat and connect it back again once in a while. And this is to force more aging on the crystals. Maybe there is something more that produces noise. There are, after all, 21 crystals, and it's enough if one of them is a little bit bad. My aging procedure has turned out to be counterproductive. The noise has increased significantly. I see now minus 125 dBc per Hertz at 1 Hertz offset. That is a degradation by 7 decibels. And of course I see the same thing in Linrad, although with a better accuracy, 125.5 at 1 Hertz offset. I stop this video here. The purpose was to show how I have improved the measurement system. Now that I destroyed the performance of the multi-crystal oscillator, that is a difficult problem to fix because there are many crystals and probably just one of them has failed. Or there could be some bad soldering or something else that has caused this. But that's a big problem, and I will not continue this video with it.